Hi, it's Matt, and here we're going to talk about the second postulate of quantum mechanics. So first off, what does the second postulate actually say? So the second postulate of quantum mechanics shows that all physical observables have a corresponding operator in quantum mechanics, and that these operators are both linear and Hermitian. You'll see we have four key terms here that we need to describe what they are, so let's do that on the subsequent slides. So first we'll talk about physical observables. A physical observable is a property that can be measured. So some examples are position. We could take, let's say we're measuring how long a table is, we could take a tape measure and measure it. So distance, or by that respect position, is a physical observable. Similarly, we could measure the momentum of an object. And to do that, we would likely measure its velocity and then multiply by the mass, or we might be able to measure the momentum as a whole. Similarly, we could measure energy and angular momentum. There are many other physical observables that we can measure, but here are just some examples. So again, a physical observable is anything that we could measure. Next, let's talk about what an operator is. So an operator we could think of as a mathematical instruction or some sort of instruction. So it tells us to do something in math. And we denote an operator with this caret symbol above a letter. So for example, the derivative with respect to x operator is given here. So we see that we have this big capital D, and that just says to take the derivative. And then we know it's with respect to x because of this x here. So we know that this is an operator, it's a mathematical instruction. We put that operator symbol, or the hat, above it. And when we place this before a function, this operator or instruction says to take the derivative of that function. So for example, the derivative of x squared plus x would be 2x plus 1. So this here tells us this operator here tells us we're going to take the derivative of what's in the parentheses, and then we'll get the result on the other side. So operators can be put next to each other. So we could have two operators, for example, or three operators next to each other, and this could be thought of as multiple instructions. So in general, operators do not commute though. So for example, if we have the B operator, which we would take first, and then the A operator that we would do after on the left side, that's not equivalent to first applying the A operator to a function and then the B operator. So that commutative property of multiplication we typically assume we do not have in the case of operators. So when we're given a list of mathematical instructions or operators, we have to be careful for which order we use them in. So now that explains what the second postulate says, that every physical observable has a corresponding operator. Now we need to move on to what type of operator we have. The first step to that is linear operators. And a linear operator is an operator that satisfies the following property. So when we apply a mathematical instruction, or this operator omega, to this sum, so C1 and C2 are going to be constants, and then F and G are going to be arbitrary functions. So we're not specifying here just two constants, two functions. When we apply the operator to this term here, we have to be able to distribute the operator into the parentheses and move the constant out of the operator. And we'll see what this means a little bit more. So what we see for it to be a linear operator is first that it could be distributed to each term of a sum. So we see we have this plus sign here. When we distribute the operator to a sum, we have to be able to distribute the operator independently to each term of the sum. And then once we do that, we also have to be able to factor out constants. So we say constants are unaffected by an operator. The other criteria we need is for an operator to be Hermitian. And what it means is that it satisfies this property here. So note that AS is all space and the star denotes the complex conjugate. So when we integrate across all space d tau, F conjugate, our operator applied to G, that needs to be the same as if we applied the operator to F and then took the conjugate multiplied by G and then integrated across all space. So we see that the key thing that being Hermitian allows us to do is move, I'll show it in red, move the operator to the other term in front of f, and then also include it when we take the complex conjugate. So just again, in other words, in the integral, moving to the operator to the other function and inside the conjugate does not change the integral's value. So in quantum mechanics, for an operator to have a corresponding physical observable, it has to satisfy both the linear property we already discussed and the Hermitian operator and the Hermitian property here. So now we're going to move on. Now that we know what the postulate says, we're going to talk about two fundamental operators we're going to use all the time in quantum mechanics. The first one is the position operator. There's many different ways we could denote this. One of the most common is r hat, and this is just used in reference to a 3D position. So whether that be x, y, and z in Cartesian coordinates or r, theta, phi in spherical coordinates, this operator here, r hat, we typically use to denote a 3D position regardless of what, I'm going to say coordinate system we're using. In one dimension, though, it's usually written as x hat, and this just is used in reference to the x position. And again, operators are instructions. So the position operator, the instruction is to multiply the function by the position. So we see that when we apply x hat to f of x, so this is applying the position operator to a function f of x, that just means multiply x, our position, by the function. So now let's talk about the linear momentum operator. This is the other fundamental operator. So here we're going to use p hat, of course p standing for momentum, and this is the general linear momentum operator. And now we're going to, just as we did on the other side, we're going to particularize to in one dimension. In one Cartesian dimension, so the momentum in the x direction, we'll denote it with a subscript x. So it's px hat, we would say. And again, this is the x momentum operator, and the instruction it gives is to multiply the function by negative IH bar and take the x derivative. So this operator here gives us this instruction. So if we apply our momentum operator in one dimension, px hat, to some function f of x, we see we're going to take the derivative of f of x and then multiply the result by negative IH bar. So now that we have these two operators, that begs the question of how do we obtain other operators? Clearly we have all these great physical observables we want to know about a quantum system. How do we get their operators? So there's a few steps we're going to use for that. The first is we're going to write the classical formula to obtain the desired quantity. So that would likely be the formula you would learn in an introductory physics course, and we'll get a little bit more into that in a moment. And then we're going to express it in terms of position and momentum. And once we have it in position and momentum, we're just going to change from the position to the position operator and the momentum to the momentum operator. So to get these quantum mechanical operators, it just becomes a matter of writing in terms of position and momentum and then writing it as operators instead of the variables. So let's try an example of this. So first, we're going to look at how to get the kinetic energy operator. So let's look at step one. Step one, we said, is to write the classical formula. So that we know from physics or from other chemistry courses is the kinetic energy. I'm going to denote kinetic energy as T, and the kinetic energy is equal to 1/2 mv squared. Now, clearly we can't just write this in terms of a velocity operator because we don't have a velocity operator. All we have is a position and a momentum operator right now. So let's see what we could do with that. So let's go to step two. We know from physics as well that the momentum is equal to the mass times the velocity. So what that means is dividing by the mass on both sides, we get that the velocity is equal to the momentum over the mass. This is great because we said we want to get from this formula here to something in terms of our position and momentum. So now we could replace our velocity with our momentum. So now we're going to plug this in. We're going to start by rewriting what we had in step one, 1/2 mv squared, and then plug in momentum over the mass for the velocity. And this gives us 1/2 m times p over m squared. We could rewrite that as mp squared over 2m squared by working out the square. And then simplifying, we get p squared over 2m. So just as kinetic energy, or T, is 1/2 mv squared, we could also write it as p squared over 2m. So now we're almost done. We just need to go to our final step, and that's to convert the momentum and the position to an operator. Note that here we don't actually have the position because the classical formula doesn't depend on it. So now step 3, we're just going to rewrite our kinetic energy, T equals p squared over 2m, and then replace our momentum with our momentum operator. So and also our kinetic energy, instead of T, we'll replace that with an operator as well. So finally, we get that our kinetic energy operator, T hat, is going to be equal to p hat squared divided by 2m. And again, this is just one example, but this is the general procedure we'd use to get any quantum mechanical, or I'll say most quantum mechanical operators. We would just base it off the position and momentum. That's all. Thank you so much for watching and have a great day. Feel free to leave any comments you have in the comments below. Thank you. Have a good day.